Good afternoon, students. It is our 21 lecture, and let me take you to the PowerPoint, and then later we will visit our exercise sample. We are at the part B of the chapter 8, and we are focusing on the frame. I would like to take you back to the textbooks of Professor Hibber, and I'm not sure do you have the file of this textbook or not. We will use this again in the course of the structural analysis. Okay. If you don't have it, you may come and visit me at my office, or you may check it out from our library. And in the textbook, there are more examples, and I would like you guys to take a look at those examples also. We're going to have 3 problems in 3 hours for our final examination. And then just like a lot of time. Yeah, this is quite a lot of time, but it's also very short time also. If you are not good at chapter 7, if you are already good at chapter 7, you are in good position. That's why I said. Now we have candidate for 2A, and another 2A but work harder. But I believe if you try, you should get it. Okay. And one of you, I try out quality, it's okay, but don't worry, you rest, okay? For the first problem, we are going to have the problem with the heat, and then the second problem, we are going to have with the frame. Now, we have to focus on the frame, okay, for this lecture. And later, we will focus on the task that's going to be the problem number 3. Most of my problem in the examination, I only take the pictures from the textbook. I didn't draw it by myself, okay? I didn't keep it by myself because I believe this type of problem international standard. And if you can resolve, you get it from us. You should meet those type of international standard also. Okay, that's all part of the textbook. I hope you guys have the textbook. And again, after finish this one, we will prepare for this one. Now, let me take you back to the frames. And as I said, for the problem of the frame in the problem number 2, we should have 2 members and 3 members. And since we limit our consideration to the structure dignity of indeterminacy 1, that means we could have only 1 independent force. Actually, we can work for 2 or 3 independent force, but that's going to be very complicated, and it should be your extra learning by yourself. For the limitation of the examination, I always think this what it is, whatever it is, should be whatever in examination. So please focus on this one. And then if you take a very close look of this one, you may see this will be fixed and roller. Fixed and roller. That's going to be one pattern. Fixed and roller. Can be 2 or 3 members. And okay, if you take a look at this one, it's going to be heat. Okay, all this quick roller and heat going to be in our scope of examination. I will make you more far away that one. And if you take the problem number 1 also, we're going to have fixed and roller, fixed and roller, fixed and roller. 3 types of fixed and roller. And then we have in roller, roller, in roller, roller. And this one, degree of indeterminacy is going to be 1. Okay. For the task, there are 2 types of statically indeterminate for the task. 1, such as this one, you have in roller. Okay. This one has UI equal to 1 because at it CE is the move force member. So CE has only one unknown. And then you have two for the hip and one for the roller. You have one. Okay, that's going to be one of your equation of equilibrium. Then this is statically integrated with one degree of indeterminacy. With what? With extra support. However, if you take a look at this one, we have what? We have hip and roller. You can use the body that has an equation of equilibrium to determine the reaction. But after you can determine the force in CD and the force in CD, you cannot determine the forces in this six member. This is internal, statically independent. Also, this one can this is internal. So, for the third problem, you got to get as what I am going to this one, or this one, that I to this one for your final examination. And usually, that's how to do it for our final examination. And we focus on consistent information. Okay, in my generation, we got to study the method, the theorem of this word. And actually, my opinion, theorem of this word is not quite powerful compared to the method of consistent information. Just let me make you more to example. Okay, in the PowerPoint, you may study about it, but let me take some of your friends that we classes study the lecture before. For the friend over here, we have in then the reaction you do the high force is going to be A sub Y, A sub X, and then C sub Y and C sub X. This one is the friend with degree of in the basic one. Then you got to select what? For example, this example, you select C sub X as your leader force. Whenever you select C sub X, you got to reduce the heat. Take this heat to the roller. Since you take the reaction C sub X out of the circle of your problem. Now, when you put this one as your leader, again, should focus again, you must check the heat to the roller with the leader for C sub X. Why? We do this because for the knowledge of chapter 7, we can only analyze the static detail. Then, when you take this one to be in and this one to be the roller, your structure is going to be statically determined. However, you have one more unknown, C sub X. And then our senior engineer, our ancestor here, they are very keen. Okay, they said by the principle of superposition, we can separate the frame in and roller, and then there are two cases. One, in and roller subjected to the different external force, and then has another same frame, but it's subjected to the linear force. And by setting linear force equal to 1 kilonewton, you will determine the reflection at point C in the linear direction. Now, if you combine this two frame together, you will get this one. Now, you got to draw the last curve at this point. Okay, you got to, I should say, you got to sketch, okay, or draw the elastic curve of the frame. This is important. You don't need to draw the elastic curve of this one. in this step. But we got to draw the elastic curve from this one. Due to the applied force, then you got to be very clear. Under application of the force, you will get delta sub V, let's say H equal to delta sub CH because no elongation or shortening of the knee. Okay, and then under the application of the force, delta sub V gonna be 0, and also delta sub CV gonna be 0, and then delta sub AX equals AH, and delta sub AB they are 0 because it is hit. For this one, you're going to have theta sub C would be 0, theta sub B would be 0, and theta sub A would be 0. And we can indicate this is going to be your theta sub A with respect to the tangential line. And also for this one, you got to draw it with respect to the tangential line. For the theta sub B, you got to draw the reference line and draw for the original to the tangential line of this one. That's going to be theta sub B. Now, you focus on what? You focus on the deformation at point C in the horizontal direction. And also, for this frame, since this frame is subjected to the force, you should draw the elastic curve with reasonable accuracy. I mean reasonable accuracy. I don't think it's going to be completely correct. Okay, you use your imaging, you use your entry sense, the same as the architectural student, they also use imaging the things here. Now, over here, you have the roller, but the roller has the C sub X to prevent the movement. So over here, you should have the compatibility condition 0 over here. And then if you say moving to the right to be positive, so they are all positive. Again, I don't think C sub X should be in this direction in my imaging. C sub X should be in this direction. I totally agree. But I took this one for the textbook. They just would like to show you if you make a wrong assumption, the problem will take care of it. And then the solution gonna be the same. Yes, you make a good assumption or bad assumption. Now, you will have C sub X equal to minus delta sub CH and then divide by F sub CC. Okay. For the same problem, Ajahn may help you. Most of the time, Ajahn may provide you one of these diffraction. But really, as we have, Ajahn would like you to be the report. If the problem is easy, I will let you be the report. But most of the time, such as this one, Ajahn provide you with one diffraction. But most of the time, again, I want to provide you with two diffraction. So practice the method of virtual working. You still have chance to make the correction. If you do not satisfy with your third midterm examination. Now, for this one, you got to start determining delta sub CH, which is going to be the fraction over here. This is on the method of virtual work. You got to put 1.0 force into this frame. You got to have another frame, and then you got to put 1.0 unit load, and then you have this 1.0 unit load have delta sub CH. That's going to be your external virtual, and the external virtual gonna be equal to the internal virtual. And what's gonna be internal virtual is going to be the integration. Why integration? Because the frame composed of the beam and the column, they are continuous structural member. Then this 1.0 unit load will produce small moment M, and the small moment M will permit the real deformation data set. However, we have the what elastic beam theory. The theta can be written into capital M. The bending moment inside this hyperframe times dx. Then this term just change it to be capital M. The theta by EI. And then your problem gonna come to your basic one. Determine capital M from this frame and determine small m from this frame. We go to the next step. Okay. Following what we should do on the analysis of capital M, you got to select upper coordinate. This is going to be important coordinate. The coordinate for capital M and for the M gonna be the same. Okay. If you say this is x1 for capital M, for the small m, you got to select the capital one also. So I skip the way you need to in the reaction and you set up this x1 for capital M. You will use this one again for the small m. Then you may put this one for the x2. That means what? That means you integrate from point A to point B. And for x2, you integrate from point C to point B. Now, basis on this one, just test it and draw the free body that can show me a bit about how you get the capital M sub 1. Okay, if you take the moment over here, this one produces no moment. Capital M will plus the term over here. This is going to be 2x1 times 2x1. And then the distance from here to here is going to be x1 divided by 2. And then basis on this one is going to be equal to 12 times x1. So your m1 is going to be x minus x1 squared and then plus 12 x1 as you have it in your PowerPoint over here. Okay. And then for the x2, do the same thing. Just one done. Summation moment equal to 0. This direction is positive. Because what? This direction is positive. You have this one capital M2 and then you have this one 6 times x2 to get the result. Okay. And then for small m, you may use these pictures because as Ajahn show you, this, I realized the pictures over there and this one is the same. Then do the same. Okay, just take this one, summation of the moment equal to 0. And then Ajahn should note that you should use the same moment direction for capital M and small m for summation of the moment equal to 0 over here. You have this small m1 equal to x1. This produces no moment, only this one. Then you may cut again for this one. You have this for small m2, summation of the moment equal to 0, and then put this direction to be positive. Small m2 is gonna be equal 1 to half x2, and then you get this one, and do the integration again. I don't know, you use the calculator to do the integration or not, but I think that's gonna help. Okay, and if you don't like it, you can do the manual integration. You get the result, and it is positive. That means what? That means delta sub CH move in the same direction of the unit here, and then go to this point. I should say you take this one because you set up C sub x equal to 1. Then the term capital N due to the applied loading to determine f sub cc gonna change into small f. And I should note that if you observe it, you will see for determining of the deflection due to the unit load, the capital M always change to the small m. And then you get this value m squared, small m squared, dx over dx. Then you only do the integration to get the result. Now, take it back to your compatibility condition. You will get C sub x to be negative. As Atlantis mentioned, the professor intended to show you if you choose the wrong direction, you get a negative value. Then make correction, put this one to show us. And again, force is the vector, is have the magnitude and direction, and also the direction slope. They are all vector, have the magnitude and direction, and I found from the midterm, the third midterm examination, some of you only provide you with the magnitude. Even as I said, magnitude and direction. Okay, you didn't provide the direction. So let me take 1.5 out of your score. Okay. And also, you didn't indicate in your calculation also, not only at the answer table. Now, you got to understand that, okay, that must put this one because the direction is important. You got to know the direction, not only the magnitude. Okay, now your starter gonna be like subject that to 6.75, and this actually is the roller. You may determine the reaction, okay, by using the knowledge from static. And again, you should know the shear direction, and I should help you sometimes the example in the textbook is not a very good example, such as this one. Okay, it didn't indicate the slope. Okay, only indicate the magnitude. And sometimes, some of you said, "Adan, how come you are so delicate like that one?" I said, if you don't tell me the slope, okay, how do you know that line gonna be something like this one? Okay, this is gonna be slope minus 2. In order is to get anything. And also this one, you should get dv by x equal to 0. And if you don't like to write this one, you like just put s equal to MOK, because s represents the slope. Okay. And also for the moment diagram, you should know this is gonna be positive. Okay, this is gonna be negative. And also you should know this is gonna be negative. Okay, so it's gonna have something about last term. Let me take you to this picture by logic by yourself. when you draw the elastic curve, then I can do to show you again. You have thin pin and you have little joint. Then, under application of the force, delta sub AX equal to delta sub AY, they are zero, no movement. And then this one also, delta sub Cx equal to delta sub Cy equal to zero. Okay. And since A and C cannot move, the point B cannot move, then there are no axial deformation for the column in the beam. Then you will have delta sub dx equal to delta sub dy equal to zero. Okay. Now, due to this type of deformation, you should be able to sketch is supposed to have this type of deformation. And for somehow the deformation reverse the direction. This is important because this point, zero moment, is the inflection point. The inflection point very important for the reinforcement concrete because you're going to use this to put the reinforcement. Now, based on this kind of deformation, you will get this deformation like this one. Now, this one must rotate due to rigidity. And then following this kind of deformation, you will get the curve like this one. Okay. Now, you may forward need more information, put the tangent line, draw this one. This is going to be center A. Okay. And then put the tangent line like this one and draw this one, draw this one. You can see the slope center B on the beam and on the column rotate in the same counterclockwise direction. And then for this one, theta sub C, you will have in this direction. This is supposed to be the last curve. And if you notice on that, no calculation at all. Is this 2 points out of 10 points to the elastic curve? I myself believe, even though we are not a good mathematicians, okay, in a solution, but this type of drawing are important because in our solution work, every time you want to draw a reasonable picture to show your technician, to show your worker, and this is going to help. Okay. Now, another thing, you should be able to draw the reinforcement just that for the reinforcement of the frame. Okay. This is upon this one. Ajahn always said, most of the time we run the steel, or the length of the structure and hook. Okay. In order us to have the way to type the stirrup. But based on the bending moment diagram, such as this one, you got to put extra steel over here. Okay, and also put the extra steel over here due to the negative, and put the extra steel over here. If this structure is the reinforced concrete. Okay, and again, due to the stirrup, negative or positive is okay, the same way, the stirrup. But you got to think, okay, this portion have low shear strength. So the spacing of the stirrup at the middle of the column may be large spacing, and then the stirrup that's close to this area and this area, you may put it closer than at the middle of the column. However, this shear is very small. So most of the time, the spacing of the shear stir over here is should have equal spacing with the maximum spacing specified in the design. Okay, and that's going to be what we should have. So the first type of the problem gonna be pivot. Okay, and then the second type of the problem going to be fixed and roller. Okay, anyway, always specify the element. For example, for this one, Ajahn will change this one. If Ajahn said A supply gonna be our resonant force, I got to take the roller out and then put the redundant A supply over here. The concept, take the roller out, replace it with the with the redundant A supply. So change the roller to the free end with the A supply. Now, our structure change to be free and fixed. That's going to be statically determinate. And then by the principle of superposition, you just separate it. Now, as you said, I take the solution from the solution manual. Sometimes solution manual is not correct. Sometimes solution manual is correct. For example, taking a force loop to this graph, you separate this graph one, we call it hybrid frame. Hybrid frame is the statically determinate frame, free and fixed and subjected to the integral. And then there is another frame subjected to the element force. And then says on this one, if you consider this portion of the frame, you will see the moment over here gonna be zero. No applied loading. Then if you cut it over here and then you draw another free body diagram, and then you can see this portion gonna have the moment equal to zero. And then if you cut it over here, okay, you will have the frame, and now the frame subject that will 50 kilonewton. And if you say this is going to be your x3, let's say this is made for x1, this is made for x2. For this one, you may have the moment of her over here. So the M3 would be zero, but the M2 is zero and M1 is zero. What is important? The portion due to the M1 and M2 gonna be straight line. And the portion for the M3 gonna be curved. And that's you should be able to know this is going to be curved. Okay, this is a curve. And then this is going to be straight line. And then this is going to be straight line. Okay, now this is going to be normal angle. And after you learn this one, you interested at point A. So this is going to be your delta sub A. And elastic curve is important because you use this to the compatibility condition. Now, let us take this one out and take a look at the second picture. Is this one correct? I don't think so. Okay. And one thing, if you do the same cut, this portion of the frame will have the moment due to A sub y. Okay, the same thing. If this have a supply, this would be 0. If this one have a supply, this one would be 0. And the same, this one would be 0. So all the vector must be bent and then is should bend out. This is not correct. It should bend out. Out of what? Out of this one. Okay, it should bend like this one. And then after that, this one still keep the normal angle. And then the deflection of the beam should be something like this curve. Okay. And then you should know that the horizontal delta sub AX and horizontal delta sub BX, they are equal. Okay, it has an equal distance. And then what you are looking for, the vertical deflection over here. Okay. Since you set A sub y equal to 1, you will get this one, F sub A. And then you have unknown A sub y. You can determine F sub A. Since it's limited from 1 million force. Then, following the same way of discussion, we will have this one 0, this one delta A. Since this is downward to be positive, then this one is upward. That's going to be negative. Okay. And again, you should be very careful. And I believe the detail of this kind of drawing help you in the future for sure. Okay. And you're going to build up your intelligence based on your practice of drawing this kind of class. So the textbook something wrong. Okay. Sometimes wrong. And then based upon this one, going back to chapter 7, you got to determine delta A and F sub A. Okay, and if the structure is simple, I may ask you to determine both, like this one. But if the structure is type of complicated, I will help you one of the deflection. So, come to the point, we are going to use our knowledge from chapter 7 and then start with the first one. Okay, that's going to be delta sub A. And again, this is going to be our delta sub A. Based on this one, you got to put 1.0 times delta sub A. So, you got to put the force. But the solution, put the force in opposite to your delta sub A. Again, the professor have intention. Okay, this one will be useful later when you determine F sub A. Okay, but don't worry. If you put the virtual force opposite to your expect deflection, you're going to get negative result. Okay, so for the capital F, if you cut this as your x1, your capital N1 gonna be 0. Then if you cut it over here and then you dot it, that's going to be the same. The capital N2 gonna be 0. And then if you cut it over here, then you draw your free body diagram. And then you mark this is your x3. This is 50 kilonewton. Then your moment in this direction, summation of the moment equal to 0. So your m3 plus 50 times x3 equal to 0. So you have m3 equal to minus 50 times x3. And this is, let's see, for this one, you just draw this portion. Then you must use the same of what? Same of coordinate. This is important. And also same of direction of capital M and small m. So you got to put this small m in the same direction, this capital M. And if you take the moment over here, you are very clear. This is M1 equal to X1. And do the same thing. Okay, you just cut this one and then you draw your elastic curve. Now you have what? You have this to be one, and this is O meter, and this is x2 by the same location of the moment over here. This is going to be small m2. You do the summation moment equal to 0 over here. So this is what? This is going to be 1 times 4. So this is going to be 4. And then you cut another cut over here. And then draw your free body diagram. That's going to be your x3. Now, your x3 going to be this one. And you have force 1 over here. And then since you use this kind of direction, this is going to be in the same as capital M. So from here to here is going to be 4 meter. Summation of the moment equal to 0 and 3 going to be 4. Okay. So at the end of this one, after you show your calculation, you're supposed to get the result. And you can see this is 0 times this one. The first term 0. And then you have another one. This is 0 times this one. This is 0. You have only one more left. That's gonna be the M3. Capital M3 times small m3. And this is negative. At the end, you get negative. And then you get the result. It's going to be opposite to the virtual 1 unit force. You state is upward. So, since it is negative, it's going to be downward. Okay, that's important of the direction. Now, for this one, F sub AA and the elastic curve is not correct. It's supposed to be something like this one. And keep this one rectangular. And then you should have this kind of deformation. And then you should know again the horizontal deflection delta sub. This is AX and delta sub BX. They are equal. So you are interested only for this F sub AA. And you should have this space also. Okay. And then for this one again, this is the same. Okay, you assume A sub y equal to 1 unit. When you assume A sub y equal to 1 unit, capital M change with small m. And then the capital M over here change to small m. And again, a note on this one is always like this one. The has also. Now, you have the M small m1, small m2, and small m3. Okay, you just put it and do the integration. Now, this is positive. So, you get the result in this actual virtual universe. And put everything together. Now, your air supply is in a correct direction. Now, your air supply is going to be 4.688. The problem over here, I should note that everybody, if Ajahn put the load in between the column and or the mean. For this one, you got to say this is gonna be x2 and this is gonna be x3. If there is no hypo, or if I can put this one to be uniformly distributed, the whole mean, the same effect can occur. You may say the coordinate along here gonna be x1. Okay, so when you get the problem number two, check whether I can put unit load. Me to read the beam, me to read the forum or not. If I can get, you got to use this kind of deformation, body. Okay, now you can determine the reaction and later you can draw your shear diagram. Okay, and again, you should put the slope with this value. Again, for the second one, you may have this kind of moment diagram. This put the slope. You may use S, okay, or you use slope like this one. If you don't like to like dm by dx, or if you don't like to write dv by dx, then put s or slope. Okay. Now, this graph has this inflection point. Okay. Inflection point. When you have inflection point, you got to indicate. And also, this is going to be positive, and this is going to be negative, and this is going to be positive. Basis upon this one, okay, roller. Since this is roller and then is subjected to the force over here, for sure, this one gonna move to this location, and you will say this is delta psi, and then the term over here gonna be delta sub dx, no axial deformation, this one equal to delta sub ax. Now, that is the inflection point over here, just below the loading point. And this is gonna curve like this one. Since this is fixed, so the curve of this one supposed to be something like this one, to be curved only portion. Then there is the inflection point market over here, which positive change to the negative. Now, this one must curve like this one. Okay, so you may select from this one, it's going to curve like this. Now, the elliptic connection gonna be over here. Okay, and since this is positive, so this is gonna be your deformation of the beam. And then this is going to be your A, B, okay, C going to be the same. And then you say delta sub AY going to be 0. And then draw the tangent line over here. You may say this is going to be your theta sub A. And with the reference over here, if you draw the tangent line with respect to your horizontal and vertical, you draw from the original to the new one. Original to the new one. You can see this is going to be theta sub B, rotate counterclockwise. And you also delta sub By equal to 0. At the end, this is fixed delta sub Cx equal to delta sub Cy equal to theta sub C equal to 0. The basis of this one we will use this again in the subject of structural analysis. Okay, we will study about slope deflection method. And by the slope deflection method, we will use this kind of knowledge, okay, to be the basis of the method. Now, Ajahn would like you, if this structure is the RC structure, how should you reinforce this structure? Now, do the same thing as before, put the frame as this one, and then this is gonna be fixed end. This is gonna be lower. Most of the time you run the steel for the beam along its length in order to hold the stirrup and have the hook in order to hide the reinforcement close to the concrete. And now, due to the positive moment over here, you may put more reinforcement in this portion, sorry, should up over here because the moment over here is large. And then for this one, you should put it over here. And then for this one, you should put it over here. This is the sketch in your head. And then for the shear, okay, this is the portion has very large shear. So the spacing of the stirrup in this portion must be very close. And for this one, the shear is low. The spacing of the stirrup may be larger than the leg move or the column. But there is no shear force over here. Could we have the stirrup in this one? The reinforcement concrete design require minimum, even though there is no shear, you have to put minimum spacing for the stirrup. So for this one, the spacing may be largest. Okay, so that's going to be the scale of the steel reinforcement. And that's supposed to be an answer, the end of this example. But there is another way to solve this problem by use the moment reaction as the resonance. Basically, we use A supply. Okay, and then we change the roller into what? Into free end. However, this one is fixed. Okay, but fixed. There are 1, 2, and then you use this one. You use this one to be your redundant. If you use M sub A as the redundant, the support still have A sub X and A sub Y. That means you got to change this one to be the key. Okay, you have to change this one to be the key. Let me put the direction of this one in this way. Now, you have the structure with pin and roller. You can use the knowledge previously learned to analyze this structure. Now, the main thing, you select M sub A. The support A is changed from the fixed to the pin with the redundant force M sub A. And you use the principle of superposition, separate this frame into two phases. However, since you use the moment as your redundant force, your compatibility equation gonna equal with the slope. That's again actually I like the redundant force in order to go with the linear diffraction. Okay, so do the same thing. This is 0. This is gonna be in this kind of clockwise direction. In this kind of clockwise direction. So you got to have M sub A with the negative. And then coming back to the same thing, you got to use the method of virtual to deal with that slope. Okay, unlike previous one, you use the method of procedure to determine linear reflection. Anyway, there are much more detail over here if you refer. For this problem, since it has the load in the middle of the column, so the column must separate into two segments. And then you got to set up the coordinate with respect to that x1, x2. But for the leaf, you can set the coordinate to be x3. But if Ajahn put the load over here, okay, you should set this one to be x4. So see this one. But since we don't have that one in this example, so only 3. And then you do the same thing, okay, compute for the capital M and compute for the small m and determine the slope, okay. You can possibly, that means you assume virtual moment for what the correct direction. Then, for the small m, you can see, for this case also, to determine the reflection due to the one unit load. The capital M take to the small m, and then just follow all of this one. This extra one, I will put in your final examination, okay, to make us more closer. And I believe if you have that, you can learn it by yourself, for sure. So, and then have more example, and I would like you to go back home and draw the elastic curve properly. And Ajahn should say, due to this portion BC, there is no moment over here. So this portion must be certain. One more thing, this is incorrect. The correct, you want to put the roller over here to make it correct. And then if you put the roller over here, this is going to be theta sub b. And this is going to be delta sub bx. And delta sub by going to be 0. For this fixed, you may say delta sub ax equal to delta sub ay equal to theta. It is 0. On this, I see no axial deformation. Okay, no axial deformation. Delta sub cx equal to delta sub cy equal to 0. And then you have the reference line over here. And then you have the tangential line over here. And over here, you have the slope of this one. Load head theta sub c in this counterclockwise direction. Okay. I believe you can imagine it and try to do your best since the scale for the spot for drawing the elastic curve as high as the shear diagram and magnetic diagram. Okay, so this putting more detail in your elastic curve. And then we also have this one, okay, in the previous one, and I believe some of the solution from the textbook may not correct, not believe of that's one. And that's going to be the end of the example of the frame. But before we move on example, they are frame with two members. Okay, in order to hold the scope of my teaching and learning, let us move to the extra example. Okay, and let me stop the record also. It's already 17. Okay, let me start show you the previous year's final examination for the frame. Okay. After I show you that how wide, okay, and then also use those kind of easier as your final examination problem, such as this one is a key. Okay, and Ajahn asks you to determine both of the diffraction required for the compact stability condition. Ajahn asks you what will be your compact stability condition, and then asks you for the diffraction of the frame. Okay, that's the base of the base. And then asks you also the reinforce piece of X, and you should put the answer in the given area. And the problem on this one, I should say, it's going to require a lot of calculation, but it's not that hard. Okay, you should finish it within an hour. And also, you may have you have been go to my video related this one also, the previous yes examination, but this one is fixed and lower. Okay, that's going to be close to the second example in the PowerPoint. And then again, you should be able to determine the required diffraction, and that's going to be finished within an hour. I already post this kind of problem to the Facebook group, but some have some kind of memory, just follow the equation. And this one also fixed and lower. Ajahn put more over here. Okay, this time if I like to put, I can put the road over here at the middle of the column. That's going to be the final examination problem. So go to the Facebook group and download and try to solve it. All of this problem already in our exercise example. Now, let me take you to this one. For the previous one, and then show you that you got to define two diffraction. But on this problem, we have the fifth square, we have E, we have I1. I said I1 because over here is I1. But this problem, the beam has the moment of inertia to half of the I1. Beware about this one. And then following is difficult to determine the reaction by consistent information, and we could use the horizontal force at point B as the resistance. Now, if you link it, you should translate the phrase, okay, by what? If you put the sub x as your resistance force, this one must change to the lower. Okay, this one must change to the lower. And then by using principle of superposition, you should be able to separate this frame into two frames. One called primary frame, and you can see this is going to be the pin at this one, and this is going to be the roller. And then you got to combine the primary frame with another frame. Since this is 4 meter footprint, 4 centimeter, and then 3, and then 2, and then the second frame will subject to only the redundant form. So you will have this one. So in combination, if you combine this two frame, you get this frame. And then basis upon this two frame, you may have the first frame with the elastic curve already. And since you use d sub x as the greater than the proper over u with the delta sub d. Okay, and this is 0.963 millimeter, and the frame over here subject to what? Subjected to d sub x, then the roller must move to the left, and that's going to be the deformation. Due to this kind of pushing, this portion of the frame should also has this kind of deformation. Okay, or to be moving to the left, and then the leading charge must shift itself to be charge, and then it is supposed to be the reasonable elastic curve of the frame. And we are looking for this one. This is going to be delta sub beta. If we use d sub x to do the calculation, if you assume d sub x equal to 1, so this can be f deflection due to d sub x equal to 1 at point D due to d sub x. Now, when you consider the elastic curve, the second consider the elastic curve. We have what? We have this one going to be 0 equal to if you set put this direction to be positive, that's going to be 0.963 millimeter. And this is in opposite direction, minus f sub dt, and then d sub x, and then your equation, your compatibility condition, the compatibility equation f d in horizontal direction is going to be what? D sub x equal to 0.963 millimeter divided by f sub dd. Okay. Now, the problem comes to the point you only need one deformation. Okay. So, next step. Number 3. Determine f sub dd. If a child would like to check it, a child can provide f sub dd and ask you to determine delta sub d. That's also possible. Okay. And then following this one by using the method of virtual or virtual method, we have what? We have the external virtual. Put this one. Okay, we may do again, and then we put the force 1.4 over here to the roller and in frame. Now, this is about this one. You have 1.0 and this one f sub dd, and then it's going to be equal to integration. Now, this one will forward with the small f. Okay, so this small f will this d theta, but this d theta equal to capital F divided by EI dx. But for this one, F sub dD, okay, F sub dD is quantity. So these are theta gonna be small m over EI dx. See, they are same. Okay, so this is gonna be small m and then dx over EI. Now, this is your routine to analyze the structure for the small m. This is upon what we have here. You should have this one for a sub x, and you also have the first located here. I believe this one supposed to be our D sub y. D sub y. Why? D sub y located clockwise, and this one located counterclockwise. So expect D sub y down in opposite direction. Since D sub y down, so A sub y gonna be upward, and then you do simply summation of the moment about A equal to 0. And this is going to be the line of action of the sub y located in clockwise direction, and this is 4 meter over here. So for the sub y, and one have the line of action over here, and the different over here. 3 meter and 2 meter, this is 1 meter. So it's gonna be equal to 1 meter. So the sub y gonna be 1/4 or 0.25. Okay. Since this is 0.25, summation of x sub y equal to 0 downward upward. This is 0.25, and then summation of x sub x equal to 0.54, and this is gonna be 1. Now, the problem comes, how do we set up the coordinate? Okay, because use the same coordinate, and then we got to set up direction of F. Now, we may think, okay, it's up to you or this state. We may say, okay, this is going to be x1, if you like to have, and then you again think that put this one to be x2, and then put this one to be x3. Okay, it's up to you. Okay, as you may do. If you set this one, and that's it, okay, this is going to be x1. So x1 going to be 0 up to 3. And then this is going to be x2. X2 is going to be 0 up to 4. And then we have this one, x3, from 0 to 2 meter, from 0 to 2 meter. This one from 0 to 4 meter. And for this one, from 0 to 3 meter. And then following what we have, yet you may move, and then you may put this one. Okay, this is going to be your portion. Let's bring to this x1, and this one subject that to 1 and subject that to 0.25. Then you may set up. This is going to be your small m1. Okay, you do the summation of the moment equal to 0. Take it over here, provide no moment. since the moment to one is load then with this n1, so this is going to be minus x1. Then coming to the second order, now we can for the x2. This is going to be for x2. The previous one that's for the x1. For the x2, this is going to be x2, and then you have this one 0.25, and this is going to be 1. Then this column over here is 3 meter. So this is 3 meter. Just take the moment over here. Put this one for M2. Summation of the moment over here to be 0. This is positive. So M2 rotate in this direction 1 unit. Okay. Rotate in the same direction plus 1 3. However, point to find rotate in opposite direction equal to 0.25 and x2. Then your m2 gonna be 0.25 x2 minus 3. Okay, I like it over here. I like it over here. And the last one, we have to cut this one. We're going to cut this one. And this is going to be in orange. And this is going to be our x3. This is something that who 1.0 uniform. And also 0.25. Now, this is going to be small m3. If you do the summation of the moment over here to be 0, or y, or to find or y moment, but 1 gonna have x3. So this is gonna be x3. Yeah. Now we come back to our virtual work equation f sub dd. Yeah. Let's find what we have. This is going to be m small m1. Integrate from 0 to 3. Integrate from 0 to 3. And this one will be minus x1 minus x1 squared. And the x1 over EI. Okay, as in the column AD has this one A. Then plus the second one, we have this M2. So integrate from this point to this point 0 to 4 and 0.25 x2 minus 3 squared. The x2 over you have it 2EI. Okay, because the heat has double moment of inertia. And then the last one, integrate from 0 to 2. Integrate from 0 to 2. This is going to be x3 squared. The x3 over EI. Okay, EI. There. When you do everything, you should get f sub dd. I got it already for over the I. The problem comes the compatibility condition. The top is in millimeter. So you got to put the EI. That's going to be 24 divided by. Coming over here, you have reality where all this one. T is 2.5. Okay, and the unit must change to kilonewton. So this is 2 over 10 power 6 kilonewton per square meter. You are okay. I would be very sharp. And then this one must change from power 6. Okay, you have this one 67.4, 67.5, and then minus 6 meter power 4. You put this one, you got 1.758 and minus b. Our computation in the unit of meter, and then this is going to be 1.759 millimeter, and this is what in this direction. Now, so then number 4, the sub x, our the sub x gonna be 0.963 millimeter divided by 1.758 millimeter. But our d sub x must be in the unit of kilonewton because we use kilonewton in our calculation. To contest one will be 0.548, 0.548 kilonewton. Now, we are ready to select. Number 5, we determine the reactions. Okay, that's going to be A sub x, A sub y, and also the sub y. And then we know shear force diagram and bending moment diagram and elastic curve. Okay. Now we have the how to determine the reaction. Okay. To make your back over here, and then this is the subject 0.548, 0.548 kilonewton, and then you may have this one for the sub y, this one for a sub x, and this one for a sub y. Okay. Take the area over here. You don't have much area. So let me move to over here. You will take the summation of the moment at point A equal to 0. Then the sub y rotate in this one 4, d sub y. And then b sub x rotate in the same direction as 0.548. That's going to be the line of action. And then the result was over here to R4. That's going to be it. And the line of action over here R2. You should have the sub y to be 3.8 6 kilonewton. This is 3.863 kilonewton. And for summation of x sub x equal to 0, you have a sub x equal to 0.548 kilonewton. And for summation of x sub y equal to 0, wow. Okay, you have a sub y equal to x. This is x minus 3.863. So your a sub y gonna be equal to 4.137 kilonewton. That's going to be the reaction. Okay, that's all. Then you got to separate your frame in order to prepare for your shear force that can move it. That you got to draw the column is 3 meters. So put it in 3 centimeters. And for the beam, 4 meters, put it 4 centimeters. And protect it to kilonewton per meter. If we put it over here. And then we also have the CD. This is 2 meters. Put it into centimeter. Over here, we have the supply to be 3.863 kilonewton, and we have the subject 0.548 kilonewton. And for this one, we have 4.137 kilonewton, and A sub X 0.548 kilonewton. And then you may zoom in, okay, then on the refined reaction. And over here, you should have the joint B, and over here, you should have the joint C. So this is A. You may see 4.378. That's going to be downward and upward. 4.137 kilonewton. And this one, you should have this one, and also this one to be 0.548 kilonewton. And then you have the moment, okay, for this one. If you take the moment to 0.548 and 3 meters counterclockwise. So you should have this M sub B, okay? Summation of the moment equal to 0, M sub B. M sub B in this direction equal to 0.548 and then hand 3. So you will have the moment over here to be 1.641 kilonewton meter. Now, this is going to be your moment. This is going to be your moment. And then this is going to be your 1.641 kilonewton meter. Then 0.548. This one 0.548 kilonewton. Then we have force over here. That's 0.548 kilonewton. And 4.137 downward. And we have this one. 4.137 kilonewton. Okay, we transfer the reaction to be the internal force. Then do the same thing for the column B3. 3.863. That's going to be this one and up this one. 3.863 kilonewton. 0.5 for F. This is going to be 0.5 for F kilonewton. Then take the moment about C. 0.5 for F gonna rotate clockwise. So you should have this moment M sub C. Summation of the moment equal to 0 M sub C. Over here. Gonna equal to 0.5 for F and 2 meter and 2. That's gonna be 1.496. Look, that's gonna be 1.496 kilonewton meter. And this is going to be your M sub C. Going to be your M sub C. And then this is going to be 1.496 kilonewton meter. Now, you have to transfer the force 3.863 up, down. And this one gonna be up 3.863 kilonewton. 0.548 in this direction, and in this direction, 0.548 kilonewton and is in equilibrium with this one. Okay, that's going to be one measure step. And then do the same thing. If you are good technique, okay, you may get fallen with this one, but you still have friend, okay, to take care of. So repeat it, and then for the chair, this is going to be kilonewton. This force is down, okay, minus 0.5 for it, and W is 0. You may say slope is 0, constant. That's going to be minus 0.5 for it, and this one, so and then for the moment diagram, this is x meter, and this is m kilonewton meter. Over here, this is p, no external moment, and then negative here. So S is going to be minus 0.5 for F. Okay, and for sure, you know the moment over here, 1.641. If you consider this is 1.641, and then this is the moment. Follow our sign dimension. They are in the same direction. So M here gonna be minus. Okay, it's gonna be minus 1.641. And this is minus 1.641. And then you get this one to be the moment data. And then the last one, we have the normal force N kilonewton compression minus 4.137, and until here constant minus 4.137. At the end, you have shear diagram. Okay, you may say SFD. You may say BMD, okay, and then you may have normal force diagram MFD. That's for the column A, B. If accurate, it should be okay, okay. My lecture may be quite boring, but let us take care of this because some of you friends not very good candidate. Next, for the beam, okay, we put this one for x meter and this one we in below the time. 4.137 going to be upward plus 4.137. The distributed load S is going to be minus 2 and this one 3.863. Actually, you should know that this 3.863 is the same as this one, but right up and cross the shear force diagram. So this is minus 3.863, and then you will have your shear force diagram like this one, and this is going to be point of zero shear force, and x over here is going to be 4.137 divided by slope. To get this one, 2.0685 for point of zero. This is important because it's going to provide maximum moment for the beam BC. And then for the moment diagram, again, this is x meter and m kilonewton meter. Counterclockwise going to be negative. So this is going to be minus 1.641. Then this is going to be S equal to, S equal to what? Here over here, 4.137. And then up until here, we have slope equal to 0. We don't know the moment over here. Moment over here minus moment over here minus 1.641 minus over here, and then that's gonna be equal to 1/2 to 5.0685 and 4.137. You will have the moment over here 2.635. Okay, 2.635 kilonewton meter. That's the V over here 2.635, and highlight it. And then the curve would be like this. Okay. And then this one is going to be negative based on our side convention. Let us back equal to 0. So let going to be negative of 1.496, and that's going to be about about 110 millimeter over here minus 1.496, and this is going to be slope over here s equal to minus 3.863. Then the curve gonna be like this. Okay, and then the last one is like to write the normal force diagram. This compressive force is going to be constant 0.548, and this one minus 0.548. Now the last one is going to be the column. So take this one and do the same thing. That's going to be your cross diagram. This is going to be my last shear cross diagram, moving diagram. For this term, next half we started as no diagram at all. Okay, so I take some half for this one because it's going to be the last visit to this one. Shear. This is going to be positive. So this is going to be up 0.548 S equal to 0 no W, and then downward process plus 0.548, and then for the moment we have X meter, this is M kilonewton meter. Since shear is going to be positive, so this is 0 S equal to 0.548. You can be very sure that the moment over here going to be positive, and this is going to be 1.496. So put it about 1 centimeter, 1.496, and then due to the positive slope, you know about the last one. Normal force compression. That's going to be N in kilonewton, and compression minus 3.863. 3.863 minus 3.863. So you have this one. And then this do one more thing. After you finish this one, is help me combine the graph. Here provide the diagram. That is try to do so by the time we have much time of this. Do we have a class name for us? And we have the okay. Anyway, this help me to the this is going to be 1.5. This is going to be 2. This is going to be 1. The shear force diagram, and then also this is 1.343 meter, 4 meter, and 2 meter. Bending moment diagram. Copy all of this and put it over here. Here. Okay, if everybody want to do it, that will take a lot of confusing now. And then the last one, we should draw the last that we put this one. Actually, you got to draw it over here, but the bending moment is close over here. This let me use the area over here to draw it. Okay, this is going to be him and him, and then subject that who kilonewton per meter, and then following what we have here is going to be very tough to predict how the structure size way. Okay, but since the column here is long, the long column when subjected to the force is going to be weaker than the shorter column. Okay, and then you will say this is going to be the direction of the size wave. This is delta sub dx and f. This is delta sub cx, and delta sub cx equal to delta sub dx. Now, that's going to be the step. This is B part. This is C part. This one, curve like this one. Curve is going to curve like this one. So, for this one, it's going to be curve like this one. Just use only a portion of it. See, it's going to be if you cross the object, the curve will find the same. And then for this one, it's gonna be curved like this one. Okay, it's gonna be curved like this one. Now, over here, if the rectangular and over here also, it's a rectangular, then this portion negative, this portion negative. So this is going to be concave downward, and this is going to be concave upward. And you got to integrate in fractional point showing. This is your integration point. And if you are really to take it, delta sub dy equal to 0, delta sub dy equal to 0, then if you can do, you will say this is going to be the slope, okay, the slope, that's going to be the slope from this one to this one. This is going to be the slope rotate like this one. It's going to be thing like this one. And this is going to be theta sub b, and this is going to be theta sub c. This is going to be theta sub a, and this is going to be theta sub d. Delta sub a equal to delta sub cy equal to 0. Dx equal to dy equal to 0. And since it's just supposed to be all, I can demonstrate to you for the frame problem and the diagram. And next time and then time, we will be talking about the task. We have only 2 hours. We have 2 extra examples, and we have 2 type 1, DOI, due to the score. Another one, degree of indeterminacy due to extra number. So, any questions? No questions? Can you continue?